Right, in this video here we're going to look at an example problem involving radioactive decay. Now, if you didn't look at the other video that I did where I explained the model for radioactive decay and what the formula is like and what all the variables represent, you probably want to check that video out before you watch this one, because there I actually explain what the equation looks like and what everything means. All right, but in this one we're just going to do an example problem. So here's our example. Polonium-210 has a half-life of 140 days. A sample has a mass of 300 milligrams. And part A, we want to find the function that models the mass remaining after T days. All right, so first common mistake people make, polonium-210, a lot of people look at this and say, well, there's that number there, 210. Where do I put that number? Is that my R? Is that my T? Is that my M sub 0? Where do I put 210? Polonium-210, that's just the name of this radioactive substance. That 210, that's not a number that we're going to be plugging into our formula. Right? Most radioactive substances have a name and a number, and that number, I think, represents like the total number of particles that it has in its nucleus or something like that. So, don't think, well, there's a 210 there, I need to put that somewhere in my formula. You don't. All right, that's just the name of it. All right, so we want to find the function that models the mass remaining. So for radioactive decay, again, if you watched that other video I did, you would know that the formula for radioactive decay is m of t equals m sub 0 times e to the negative RT. All right, that's our basic model for radioactive decay, and what I need to do is plug in numbers for my m sub 0, my initial amount, and my R, which is my decay rate, my relative decay rate. All right, so m sub 0, that's pretty easy. That's my initial amount. Well, they tell me that the mass has an initial amount of 300 milligrams. That's what we're starting with. So that 300 is going to be my m sub 0. All right, so I can do m of t equals 300 e, and now we need to figure out what R is. All right, well, recall, and also from that other video that I did where I explained this formula, we have a formula for finding the relative decay rate if they give us the half-life of the substance. And that formula is R equals ln of 2 divided by h, where h is the half-life. Right, so radioactive decay, there's like this extra formula that sometimes you need to know in order to be able to figure out what R is. Right, so that's going to equal ln of 2 divided by the half-life of 140 days. And then I'm going to put that into my calculator. So ln 2 divided by 140 gives me 0.004951. So let's call it 0.00495. Seems like a good place to round that off. So that's my R value. That's my relative decay rate for this particular radioactive decay problem. All right, and that's for polonium-210, that's going to be what the decay rate is, because polonium-210 has a half-life of 140 days, so it's always going to give us that same R value. So it's m of t equals 300 e to the negative 0.00495 t. Right, there's my model for this particular sample of polonium-210. And if you watch the video that I did where I did an example of exponential growth, what we did here was pretty similar. For exponential growth, we didn't have to use this extra formula to calculate R. They gave us the R value in the problem. We just had to plug the number in. Remember, the major difference in the formulas between exponential growth and radioactive decay is the exponent, right? For exponential growth, the exponent doesn't have that negative there because exponential growth is an increasing function. For radioactive decay, since it's decreasing over time, in order to make our exponential function decrease, we make the exponent negative. Right? If I do an exponential thing to a negative power, that gives us a decreasing function, and so that's why the exponent for radioactive decay is negative, whereas for exponential growth it's positive. Other than that, the two formulas are very similar to each other. All right, so here's our model. We got our initial amount. They gave us that amount. Our R, our relative decay rate, we got that from the half-life using this little formula here. All right, so what I'm going to do here is pause the recording and erase a lot of this stuff, put the formula back up, and then do the next couple parts of this problem where they ask us to use this equation now to answer some questions. All right, so I put our model that we found up at the top here, m of t equals 300 e to the negative 0.00495 t, where m of t is in the milligrams of this radioactive substance, and t is measured in days. Remember, when we're doing a model of a real-life situation, we not only need the equation itself, but also what our variables represent and the units that we put on those variables it's going to make it easier for us to do the other things that we need to do with this model. It's also, if we have to communicate this to somebody else, if we just tell them the equation, but we don't tell them that what t and m of t represent, they don't know how to use that model to actually do anything with it, right? So you need to not just have the model, but also what the variables represent, what units do you have to use for it, so that it's useful for people to actually use that model to answer questions. All right, so here's our next question. Find the mass remaining after 1 year. All right, not too hard to do, but one little tricky thing, right? So obviously they're giving us a unit of time here, 1 year. So you would think, well, 1, I plug that in for t, and then I do the calculation. But remember, t is measured in days, not in years. Again, it's important to have the units there so you don't get mixed up with stuff like this, right? So 1 year, I have to put that into days before I plug the number into the equation there, right? So my t value in this case is not going to be 1, it's going to be 365 days. Right? Hopefully we all know that there are 365 days in a year. We're assuming that it's not a leap year, right? So 365 days in the year. So that's the number I need to plug in for t. All right, so I'm finding m of 365, right? Which is 300 times e to the negative 0.00495 times 365. And anytime we're doing a problem that involves the exponential function, the e raised to a power, if we have to do a calculation, we're going to have to use a calculator to actually figure out what that's equal to. All right, so I'm just going to type it in, 300 e raised to the power negative 0.00495 times 365. All right, I'm just double checking because I just typed in a whole bunch of stuff, and I was also talking while I was doing it, and sometimes when I talk and type at the same time, I talk wrong and I also type wrong. But this time I did both pretty well, I think. So there's what I type in. Notice this whole exponent here, this number times the 365, when I put that in the calculator, I put the whole thing in one single parentheses to make sure that my calculator does it correctly, right? And to get an explanation of why I have to do that and what happens if I don't do that, check out the video that I did, the example on the exponential growth problem, the population growth problem, because I explain it in more detail there why you have to do it this way. But anyway, when I do this, I get 49.256, so my mass is going to be about 49.3, let's say, milligrams, right? Because my m of t, my mass, is measured in milligrams, and so after, what do we say, 1 year, I go from 300 milligrams down to 49.3 milligrams of this radioactive substance, all right? Which makes sense because my half-life is 140 days. Remember, half-life means half of it goes away in that time. So in 140 days, I would be from 300 down to 150. In another 140 days, which would be 280 days later, I would be from 150 down to 75. So then a year, if I add another 140 to that, that's a little bit, this would be a little bit less than that next half-life. So you can kind of use the half-life to kind of get an estimate of whether your answer makes sense. All right, because remember, after every 140 days, the amount gets cut in half. All right. Hopefully that made sense what I was just saying there. Okay, so again, when you're doing a problem like this, they give you a number, you have the equation. You just got to figure out, is that 1 year, is that my t, or is that my m of t? It's my t, it's my time value, right? I'm looking for the mass, so I'm trying to solve for m of t, but I have to change those years into days to make sure I have the correct units to match up with the rest of the problem. And once you get that, you just plug in the number in this case. When you're plugging in the number for t, it's just putting the number in there and then popping it in your calculator to get the result for it. All right, so that's our mass remaining after 1 year. I'm going to once again pause this, and then I'll put up the next part of this problem that we'll take a look at. All right, so part C now, we want to know how long will it take for this mass to decay to a mass of 200 milligrams. All right, so once again, we got our model. They give us a number 200. I just got to decide where to put that number. It's 200 milligrams. It's my mass, which is my m of t. Right? Don't plug in 200 milligrams for t like we did back in part B where we plugged in 365 days in for t. Right? 200 milligrams is not a unit of time. It doesn't make sense to plug that in for t. Right? Remember, when you're doing these word problems, you have to read them carefully, know what the variables represent, and make sure you're plugging the numbers in for the correct variable. Right? 200 milligrams, that's my m of t. That's my mass. So that number has to go over here for the m of t. All right, so I do 200 equals 300 e to the negative 0.00495 t. All right, and now how long means I'm solving for time, which is good that my variable time is still in there. That's what I need to solve for. All right, so my variable that I'm solving for is in the exponent of my e, which means I have an exponential equation. So I have to go back to, how do I solve an exponential equation? And if you didn't watch the couple videos I did about solving exponential equations, you should check those out because it's used a lot when we're doing these, obviously these applications of exponential functions. We end up solving exponential functions a lot when we're doing that. Right? So to solve the exponential function, step one, isolate the exponential term. Right? This e to a power has to be by itself, which means I divide that 300 to the other side, which 200 divided by 300, those zeros cancel out, and I get 2/3 equals e to the negative 0.00495 t, right? And then once I get that e to the power by itself, I do the natural log to both sides of the equation. So the natural log of 2/3 equals the natural log of e to the negative 0.00495 t. And sometimes the worst part about doing these problems is having to write out those long numbers step after step after step. It's kind of a pain, right? But when we do that natural log, the reason we do that is because the natural log will cancel out the e, right? Those are inverses of each other. That's why we do the ln on both sides. It cancels out that e every time. All right, so I get ln of 2/3 equals, let me put this up here. All right, so the ln of 2/3 equals negative 0.00495 t. And then I divide by that big negative number. I'm not even going to write it again because I'm already sick of it. So I do ln of 2/3 divided by that negative 0.00495, and that's going to give me my value for t. Right now, when we did solving just regular exponential equations, we talked about giving the exact answer, the exact value of your solution, which would be ln of 2/3 over negative 0.00495. However, if we are doing an actual word problem that relates to a real-life situation, generally we want to give our answers not in the exact form, but in decimal form. Like, we're not going to walk around telling people, oh, to get down to 200 milligrams, it's going to take ln of 2/3 divided by negative 0.00495 days. Nobody knows how many days that is, right? That doesn't make sense to most people, right? Even people who are really good at math, you tell them that, they're like, I don't know what that means. I know how to figure it out, but I don't know what it means just off the top of my head, right? So for a problem like this, for a word problem, we want to type that in. So ln of 2/3 divided by negative 0.00495, and we get about 81.912 days, right? So t is approximately equal to, since it's 81.9, let's call that 82 days. Right, so it will take approximately 82 days for this mass to decay from 300 milligrams down to 200 milligrams. All right, so yeah, when you're doing these problems, the first thing that we did in part A is getting that model and having it set up correctly. And then it's, for each interval, for part B and part C, are they giving me the t or are they giving me the m of t? If they give me the t, like in part B, I just plug the number in and put it in the calculator. If they give me the m of t, like in part C, I actually then have to go through the steps of solving that exponential equation to get my answer. All right, so I'm going to pause this one more time, and then part D of this is to actually graph this function. So I'll just put up the graph and then talk about it real quick, and then that will be the end of this example. All right, so for part D of this problem, I put the graph of the function up here. So graphing this function that we found in part A, what I did is basically I just marked off 3 points that we knew. I knew the initial amount when t was equal to 0, it was 300. So I put that point up there, 0, 300. I knew that after 365 days, it was 49.3. So way down here at 365, I have 49.3. All right, so 365 comma 49.3. And then from part C, at 82 days, it was at 200. So I went to 82 days, and then up here to 200. And then I just used those 3 points to draw that, that decreasing exponential function. And, that's our model of the decay of this, whatever it was, polonium something substance. Right, and I also put on the graph here, just to kind of piggyback on what I was talking about a couple minutes ago, the half-lives. Right, remember the half-life was for this substance was 140 days. So after 140 days, half of the original amount should be still there. So we started with 300, so after 140 days, it should be down to 150. And then after another 140 days, so when t is equal to 280, half of the 150 is 75, so that's where the point should be at 280 days, so it should be down to 75. So you can kind of use those, those half-life markers along the way to check to see if your answers are making sense. After 82 days, that's less than the 140 half-life, so that answer should be above 150. which was half of that 300. So hopefully that makes sense to you. All right, there's an example of radioactive decay.